Hello everyone. In this lecture, we will study complex frequency domain analysis for continuous time signals and systems. For signals, we will study these contents. For systems, we will study these contents. First, why do introduce the complex frequency domain analysis for continuous time signals and systems? Here is the system described by this differential equation. How to obtain the zero input response and zero state response for this system. In time domain, we use this homogeneous equation to get the zero input response, and by convolution to get the zero state response. In frequency domain, we can use this equation to get zero state response. But we need the input signal x of t is absolutely integrable, and the system is stable. Similarly, how to describe the properties of the LTI system? In time domain, we can describe it by the impulse response. In frequency domain, we describe the system by the frequency response xj omega. But this is only suitable for stable systems. So there are some restrictions to time domain analysis and frequency domain analysis. First, we will study the complex frequency domain analysis for signals. First, we will discuss S-domain representation for continuous time signals. We will study Laplace transform of continuous time signals, definition of unilateral Laplace transform, region of convergence of Laplace transform. For this exponential signal, how to get its Fourier transform? If alpha is greater than 0, we have known this exponential signal doesn't exist the Fourier transform. However, if we multiply x of t by exponential signal, we can do the transform again. If this condition is satisfied, we can get this expression. Here, S is a complex frequency variable. S equals sigma plus j omega. Generalizing the idea we can get, let S equals sigma plus j omega. You can get this x of s. According to the inverse Fourier transform, we can derive the inverse Laplace transform of x of s. Xt equals this expression formula. From this expression formula, we can find continuous time signal can be represented as complex exponential function. This is the definition of Laplace transform for signal x of t. Obviously, x of s is a function of complex frequency, S. We can use this symbol to represent the Laplace transform. Laplace is a mathematician and astronomer, French. Most systems in engineering application are causal systems. To describe these systems and solve differential equations with initial conditions conveniently, unilateral Laplace transform is defined. Here, the lower limit of integral is 0. Laplace transform is the Fourier transform of this signal. Hence, a necessary condition for convergence of the Laplace transform is the absolute integrability of this signal. The region of sigma for which this condition is satisfied is termed the region of convergence, ROC, of the Laplace transform. For unilateral Laplace transform, the necessary condition for convergence is defined as this equation. Similarly, the region of sigma for which the Laplace transform convergence is termed the region of convergence. ROC can be depicted in a complex plane. We term it S-plane. This is a left half plane. This is the right half plane. The shaded region is ROC. Here, the sigma 0 is a real number. For example, find the unilateral Laplace transform and its ROC of this signal. According to the definition, we can get this equation. You can do the integration and get the result. Here, there is no restriction to the S. So, the ROC is the entire S-plane. For example, find this signal unilateral Laplace transform and its ROC. According to the definition, we can get this expression formula. Here, if we satisfy this condition, we can get this one. So, the ROC for this Laplace transform is RE of S is greater than 2. We can describe it in this picture. Here is 2. In summary, complex frequency domain representation for continuous time signals. Signal x of t can be represented by complex exponential signal. Here is the unilateral Laplace transform definition and its region of convergence. That's all for today. See you later.